So the last talk will be given by Kenneth Rogale on the efficient discovery of actual causality in stochastic systems. It's fine. Okay.
All right, thank you for the introduction. Today I'm going to be presenting the efficient discovery of actual causality in stochastic systems, and this was done also alongside my co-author Arshia and our advisor Borzoo. So why do we care about causality? Well, in a lot of cases it can help us understand why particular cases fail. For example, one of our running examples is a mountain car that is stuck in a valley, and its goal is to reach the top of the hill on the right-hand side. And if it does so within the allotted time, that's considered a successful case. However, if it does not, then that's considered a failure. And we're interested in trying to explain what led to this failure. However, many cyber-physical systems operate in more stochastic environments, subject to noise and disturbances. So accelerating in the same position in two different runs might not necessarily lead in the same next state's position. And identifying the cause of such specific events in stochastic systems can be quite difficult. So the notion of causality that we're interested in is called actual causality, and it's proposed by Halpern and Pearl, and that's specifically looking for cases in the token case, which is this specific this specific failure was caused by this specific cause. For example, for the mountain car, why would it fail to reach the destination in that particular case would be such a question. And this definition, however, is limited to only non-probabilistic cases. So in order to handle stochasticity, we need to work with a different notion introduced by Fenton-Glynn, which is an extension to AC called probabilistic actual causality. In order to model such systems with noise, we chose to use discrete time Markov chains. And we can consider these to be acyclic in our case, as since we treat time as a variable, cycles are not possible, since two states at the same position occurring at different time steps are considered distinct. As you can see at the bottom, every time there's a transition, t also increments. And each path in this DTMC represents an experiment, and the probabilities reflect the frequency of the occurrence. And success and failure states are absorbing states, as we don't really care what happens after that for our purposes, and we are going to label these as halt. So what we did was we applied this notion of probabilistic actual causality and adopted it to work with discrete time Markov chains. We formulated the discovery of these probabilistic actual causes as an SMT problem. And finally, we applied an abstraction refinement technique in order to handle larger model sizes. Probabilistic actual causality specifically calls for two different constraints, first of which is rather intuitive, and that's simply that there is a scenario that occurs where the cause occurs and then afterwards the effect occurs, and that's going to be considered the actual world. And the second constraint is a little more complicated, but it says that for any counterfactual scenario where the cause does not occur, but the effect does, and all variables within the contingency W agree between the two, the probability of the counterfactual world must be strictly lower than that of the actual world. For example, if we were to select this state as our cause and this state as our effect, it would take a distribution something like this in order to make a PC2 hold. And in order to formalize this for DTMCs, we're going to use hyper-PCTL. And starting with the actual world, we're going to formulate it as this, saying that there is a cause that occurs and a subsequent effect eventually occurs. However, we also want to specify that there's no effect that happens before that cause, and we are interested in the probability of this case happening. For the counterfactual world, we are going to encode it such that we don't want to see the cause until we see the effect. And then, as in PC2, we want to ensure that the actual world happens with greater probability than that of the counterfactual world. And for the contingencies, we want to say that for all variables within the set W, they agree between the actual world and the counterfactual world. Sorry. And that's going to hold with probability 1. And finally, we want to say that there exists an actual world that the probability is greater than all counterfactual worlds. For example, if you take a look at this DTMC, which represents the mountain car example from the beginning, and we want to reach a goal of at least 0.6 on position, each state's going to have a position, a velocity, and an action. Here you can see is our initial state at time 0. And at the bottom, you can see that there's going to be 5 different absorbing states, 2 of which are considered phi e, or effect, as they do not reach the goal position within the allotted time. And using our definition, we can find that S1 can be identified as an actual cause of phi e, as if we evaluate the actual world, we get 0.345, whereas for the counterfactual world, we only get 0.15. Also, for this case, since W is empty, we can trivially satisfy the contingencies. As for the problem we want to answer, is given a DTMC representing our causal model and a predicate, phi e, representing our effect, can we find a phi c such that it satisfies our definition of PEC? In order to do so, we encoded it as an SMT problem. And we'll go through this step by step. For the actual world, we are going to create a variable for each state. And we're going to assign that to 1 if the state is in the cause and if its reachability to the effect is greater than 0. We're going to set it to 0 if the state is not in the cause and the state is either halting or in the effect, or if the reachability from that state to the effect is 0. And finally, for all other states not in the effect, we're going to propagate these values backwards through the transition system. Now, to calculate that reachability of effect, we also are going to define another variable for each state, in which it is going to be set to 1 if the state is in the effect. It's going to be set to 0 if the state is not in the effect and it's halting. Or otherwise, once again, we're going to propagate the other values through the transition system. Moving on to the counterfactual world, we are once again going to define a state variable for each state representing this probability, and we're going to set it to 1 if the state satisfies phi e, 0 if the state is not in the effect and it is halting or in the cause, and otherwise we are going to propagate the probability through the transition system for all states that are not in the cause. Now, in order to encode the contingencies, we are going to require stutter trace equivalence for W, as the differences in sampling times between the actual world and counterfactual worlds might not be the same always, but that doesn't mean that we can't reason against them. And in order to encode that, we came up with this formula where we say that for all pairs of paths in the model from the initial state to a halting state, they must be stutter trace equivalent. And in order to encode that, essentially what we do is we partition each trace into a number of contiguous blocks in which we require each state to be equivalent on W for every variable within W. And this first term says that the first states of each of these cuts is going to agree on W with each other between the actual and counterfactual world. And then for each state in each block will also agree with the first state in its own block. However, this does not necessarily work well for larger models. In some of our test cases, we have about 6,500 states, and it takes longer than an hour to solve. So we needed to use other techniques to handle more realistically sized models. In this case, we chose to use abstraction refinement. And when we abstract our DTMC, we end up grouping multiple concrete states together into one abstract state. But that introduces a new source of non-determinism, as when we're transitioning from that abstract state, how do we know which distribution to use? So the abstract model ends up becoming a Markov decision process where each concrete state transition becomes an action. For example, if we were to have these three states here and we wanted to group them together into an abstract state, we would end up with something like this, where each one of these concrete states is going to have an action. And for example, since state 1 only goes to other states in the abstract state, is going to loop on itself, whereas the other two are going to remain as they were before. In order to handle our abstraction refinement, we are first going to introduce a predicate abstraction, which we come up with a set of predicates which we apply to the DTMC in order to group it into a number of abstract states. Next, we're going to apply an SMT solver to identify potential causes within this new abstracted MDP. And finally, if no cause is identified in the abstract model, we're going to refine that model by partitioning one of the states that we have into a new set of concrete states. And the algorithm will terminate once either a cause is found or once the abstracted model is fully concretized back to the DTMC. For example, going back to the mountain car example, if we were to come up with predicates such as this on velocity and position, the resulting abstracted MDP would be this, where you can see the halt states are grouped together, particularly the failure cases are grouped together. But if we were to apply our SMT solver to this abstracted model, we would not actually be able to find a cause. So if we were to select state S hat 1 and choose that to refine it, we would end up breaking that into its constituent states. And then we would end up running our SMT solver once again. And then in this case, we would actually be able to identify S hat 1, as an actual cause. However, once we're working with MDPs, our original encoding no longer works for the SMT solver. So we need to also adapt our encoding for that. So just quickly going over the previous encodings and how we updated them. We're interested in minimizing the probability for the actual world and maximizing the probability for the counterfactual world so that we can guarantee that PC1 and PC2 still hold. For reachability of the effect in the actual world, we simply select actions as to minimize this probability through the MDP. Likewise, for the actual world, once again, for the overall term, we are going to minimize the actions that we take in order to minimize the probability. And finally, for the counterfactual world, we are going to select actions as to maximize the probability of the counterfactual world. However, when we're working with abstraction, we also need to consider how we're handling our contingencies. And we consider two different options, the first of which is going to be subgraph enumeration, where we look at all pairs of subgraphs in which all traces are stutter equivalent with respect to W, meaning that we don't have to worry about W in that case, as long as we make sure the subgraphs agree on it. Or the other option is we can look at W-preserving abstractions, where we require the abstraction function to preserve the equality of the computation trees with respect to W, and in order to do that, we would have to encode it as follows, where this simply says that all pairs of schedulers in the set of finite schedulers, and for all paths from initial to halting in the induced DTMC, are stutter trace equivalent. Additionally, when we're looking at refining states in our abstraction refinement, we also need to choose which state to use in order to break up into its concrete states. And the first option we have is choosing the state with the highest number of actions, meaning it contains the largest number of concrete states. And the other option we have is by selecting the state with the largest range of reachability to the effect. In addition to our mountain car example from earlier, we also have two other case studies, the first of which is a Lunar Lander, which is a 2D moon landing simulation that has a number of variables, and the goal is to safely land between two positions on the ground and also without tipping over. If failure here occurs when the lander either tips over or does not land at the designated area within the time frame. Our other case study is a little more complicated. It's an F-16 flight simulator, which models the outer loop controller of a fighter jet with two different test scenarios. The first one's going to be an engine test, which simply tries to achieve a target velocity. And the other one is going to be a climb test, where it attempts to reach a target altitude within the allotted time. However, both of these also are subject to a number of different safety constraints, such as G-force or angle of attack, and failure occurs when the target is either not reached or one of these safety constraints is violated at any point. If we were to look in detail at one of the cases that we did for the second scenario of the F-16, so the altitude one, in this case, our goal is to reach an altitude window of about 1,400 feet, plus or minus 50. And our algorithm was able to identify this particular state as a cause. As you can see, all four of the states that it reaches from there actually are failures, as all four of them violate the G-force constraint. And additionally, two more of them are also unable to achieve the target altitude. If we were to look at the counterfactual world, so the alternate states that it could have taken instead of those, we can see that almost all of them are able to achieve the goal after a certain number of steps, except for one, which ended up violating the g-force constraint once again. So it's rather clear that with the actual world having a probability of 1, that is quite greater than that of the counterfactual world in this case. Now looking at more results from the other case studies that we did. This column here can show you the size of each experiment in terms of the number of states in the DTMC. This column is going to give the timings for the concrete DTMC solver, the original SMT encoding. And then these two columns are going to give you the times for the MDP solver. And the one on the left is going to be selecting the state to refine with the largest number of actions. And the value on the right-hand side is going to be when we select the one with the largest reachability range. As you can see, most of these cases, the abstraction refinement method greatly outperforms that of the concrete. However, if the model is sufficiently small, then the overhead induced by using abstraction refinement outweighs the benefits, and in these two cases, the concrete model was slightly faster. For the F16 scenarios, you can see as the models get larger, especially on these, the benefits of using the abstraction refinement are a lot greater than that of the concrete solver. So reviewing what we covered, we formalized probabilistic actual causality to work with DTMCs. We applied an abstraction refinement technique that is compatible with PAC for DTMCs. We formulated an SMT problem for both finding actual causes in DTMCs and in MDPs. And we saw that based on our experiments in 3 different case studies, the performance is much better for the abstraction refinement as compared to the concrete one. As for future work, we're also looking at how we could do this when the original system is an MDP, so we can also handle non-determinism in addition to stochasticity. Finding causes in POM DPs, investigating performance for reinforcement learning and large language models for discovering actual causes or for probabilistic actual causes. And finally, for finding the actual cause of out-of-range outputs from neural networks in interest of finding how we could repair them. All right, thank you.
So there is a large room for questions, please. Okay, let's see.
So you're doing this reduction to SMT, so what particular SMT theory are you reducing to?
I'm not sure, I'm sorry.
So you just say anything, or?
No, sorry, my co-author.
Okay.
Yeah, sorry, he's the one that worked specifically with that part.
Okay.
I can probably answer. So it's the integer linear arithmetic with uninterpreted functions. So we specify free or no, with quantification. With quantification. Yeah, because the actual world is existentially quantified, the counterfactual world is universally quantified. And we specify the effect as a predicate, and then the cause as an uninterpreted function where the interpretation gives you the predicate for cause.
Okay, and maybe one more question. So which solver are you using?
We're using Z3.
Z3, okay, thank you.
So
Just a quick follow-up question. So if it's a QF Lia, so what's the plus for? Do you use plus for what again?
Sorry?
No, I think I'm asking
Oh,
you.
I'm sorry. Yeah.
So if it's a reduction to QF Lia, right? So what do you use the plus for again?
And uninterpreted functions.
Yeah, QF
It's
Lia
not
plus uninterpreted functions.
It's quantified.
Yeah. So
they are
okay, all right.
quantifiers.
Quantified Lia. Okay, so what is the plus for?
What do you mean plus?
Because you have addition, right? So the addition is used for.
Yeah. So you need to add probabilities, right, for reachability.
Okay, but is it integers then in this case? Or?
No, it's not integer.
So it's like real arithmetic?
Real,
Okay. Do you need any multiplications at all or not really?
Yes, so you need to add and you need to multiply probabilities.
Okay, so then it's like
So
linear
each
integer,
path you
non-linear
multiply
arithmetic, right?
probabilities, and then you have to add the probabilities of different paths, right, for
Okay.
reachability.
Yeah. So that's like non-linear arithmetic then.
Yeah.
Thanks.
Did I say linear?
Yes.
I am jet lagged.
It was. Okay. Other questions?
I have one. I'll just be loud. This is maybe a nitpick, but why do you existentially quantify the factual world? It seems like in a lot of these cases you'd be interested in a particular. You described it as being interested in a particular failure case, but it seems like the problem you're solving is, can I find a factual world such that there is an actual cause? Just wondered why you framed it that way.
Sorry. The framework itself that we're working with works with specific causes. In our case, the specific the specific failure we're looking for is the failures in this particular DTMC, in this model.
I see. So the factual is in some sense a run of the model.
Yes.
Okay.
Other questions?
Great presentation. I had a question about your results. Could you actually go back? Because
Sure.
I wanted to make sure I saw them right. Otherwise my question will not make sense.
Which page?
Let's see here, this page, and then we go back one other page. Okay, yeah. So I guess my question is so in these two first test cases, we see that both for Mountain Car and for Lunar Lander, we get up to seeing about, like, for Mountain Car, 27,000 states, and for the Lunar Lander, about 47,000. But the time here, the execution time in that, even for the concrete, is quite short. Whereas if you go to the next slide,
Right.
we're seeing like a lower number of states. Like for the F-16 first one, we're seeing about 13,000 and 6,000 for the next one. But the execution time is just much longer. So I was kind of curious, what's the intuition for that? Does this one just have more transitions, or what's the cause of that greatly increased execution time?
So I think it's in two parts. The first one is going to be the F-16 scenario does typically end up with more transitions. However, it also has a lot larger number of state variables.
Mm-hmm. Okay. Cool. Thank you.
I have a question also
Sure.
on this table. How you choose, in fact, the starting predicates for this abstraction refinement? So this is important in this work because it's not somehow said.
Right. So the performance really does get impacted by the choice of the initial predicates. For our case, we experimented with finding a reasonable one to use across each case specifically, not line by line, but each case study.
Other questions? So one short question, Steve. Okay. It seems that we are done. Okay, thanks. Thanks.